Hello everyone. So today we are going to discuss isomorphism in graph theory and a problem in it. So we are given which pair of graphs in the following figure are isomorphic. Show that, right? For this, the isomorphic pair give an appropriate one-to-one correspondence. So not only we have to prove that out of these PQR, two of them are isomers, but also we need to prove that there is one-to-one correspondence. So for identifying any of these to be isomorphic, there should be equal number of vertices in the two graphs, equal number of edges, and the degree sequence, which we will discuss, should be same in ascending order, and then there should also exist one-to-one correspondence. Then we may say that the graphs are isomorphic. So let's begin. So P has 10 vertices, Q has 10 vertices, and R has 10 vertices. If we talk about edges, P also has 15 edges, Q as well has 15 edges, and R also has 15 edges. So then we come to degree sequence. Degree sequence is basically the degree of the vertices arranged in ascending order, right? So this is degree sequence. So if we come below, so P, if we see P, all the vertices are of degree 3. So all of them have degree 3, 10 times, right? Similarly, Q has 3 in all the vertices, and similarly R. Okay, so all of them have the same degree sequence. Till now, all of them seem isomorphic by the definition, but now we need to look closely. So if we see that P has 5 cycles, each cycle consists of 5 vertices. Q also has 5 cycles and each cycle consists of 5 vertices, but R does not. Let's see why. If we see here, this is a cycle, right? Similarly, here will be another cycle, right? Here will be another cycle, and you can just map it accordingly. So there will be 5 outer cycles, right? Similarly, here this is a 5 cycle, this is a 5 cycle, this is a 5 cycle, right? This is a 5 cycle, this is a 5 cycle. So these are some of the cycles which you can detect, but in this graph you see that there is a 4 cycle also present here, right? So which may cause difficulty while making degree sequence, because we know that the distances between the vertices also need to be considered when we are talking about one-to-one correspondence. So clearly R is not an isomer, but these two can be. So we need to check one-to-one correspondence. So first we will check that, like in this graph, if we see that if we see two vertices 1 and 2, right? So this graph has 6 vertices, right? 1, 2, 3, 4, 5, 6. And if we go for the another side, like here, so then we have 5 vertices, 1, 2, 3, 4, 5, right? So this is a clear cut way to like differentiate between the two sides of the particular edge. And now if we look here, 1, 2, 3, 4, 5, 6. So there are 6 vertices here, right? And then here we will see that there are 5. So I will not do that again, it goes up, right? So here it has 5. So here these two vertices have perfect correspondence, one-to-one correspondence, because they are segregating it into two, means we can segregate it into two sides of the edge, and we can map all other vertices accordingly. So these two are a perfect match. After that, let us consider this vertex, right? So we point it in the main graph, we point it is 3. Now what we need to do is, for all the new paths with the edges, with the vertices we have already been attached into the graph Q, like 1 and 2, we need to calculate the distance. That is, we need to calculate the distance 1 to 3 and 2 to 3. So if we see 1 to 3 distance, it is 1 and 3, right? You see 1 and 3, so only one vertex is in middle, so here it is 1. Then we have 1 to 2 to this vertex, and then 3, means only 2 vertices are coming in between, so this is that 2. And we also need to remember that we are crossing the vertex 2 while reaching to 3. After that we have another path, basically starting from 1, then this vertex, and then this vertex. So this will be the path, right? So then we have 2 again. So I consider taking 3 paths as sufficient to declare it as a particular sequence which we need to follow in another graph. Similarly for 2, we will have 1, 2 and 2. So let's see those. 2 to 3. So 1 we have this to this, then this, right? From here to here, then this. Okay, then we have 2. So a 2 will be this to this, and then this. So there are 2 vertices, right? Another one we will have from here to here, and then here, which will have 1 in the middle. So then it will be 1 to 2, and we need to remember that we are crossing 1 as well, right? So if we see in this graph, from 1 to 3 we have 1, then we have for 2 we will have 1, 2 and 3. So we are crossing 2 vertices, and we are also crossing 2. Then we will have another 2. So another 2 will be like from here to here, then here, and then to here. So we are again crossing 2 vertices, so this is also a valid path. So then 1 to 3 exists here, and it is perfectly coinciding to this vertex. Similarly for 2 we will also get, see, 2 we got 1. Then for 2 again we will have this path, because 2 vertices are there, right? Then on the last one we will have this one, this and this. So we will have 2 vertices including vertex 1. So then this is a perfect place for 3. So we got 3, and now we can tell that 3 is correctly placed with 1-to-1 correspondence in the first and second graph. Similarly we will do for 4, but remember, when we will do for 4, we just need to check these paths, not those like 3 to 2 and 1 to 2, because they are already checked in the previous graphs. So we just need to make sure that these 3 are in alignment, and means we also need to find that they are crossing the same vertices in order, like 3 to 4 is crossing 1 and 2, so it is taking 2 vertices in between. Okay, so now 4 is also accurately placed, like 4 was here, so 4 is here in the Q graph. Similarly, after all the steps, we will have this particular 1-to-1 correspondence, where each vertex is perfectly has perfect 1-to-1 correspondence with the previous graph. So I hope you understood what I tried to explain. Thank you.